In this course, we are going to study differential equations. What is a differential equation? A differential equation is an equation or a relation between a function and its derivative. So, for example, let's consider y, which is a function of t, and an equation or a differential equation that is dy dt, that is the derivative of y with respect to t, say that equals k times y, where k is a constant. So this differential equation is about 200 years old, and this is due to Thomas Malthus. And what it's doing is this, that it's giving us a model for population growth, where y is the population at time t. We shall take it up again a little later. So let's take another example in which an object is projected vertically upwards from Earth, and the projection of and after the projection, the motion depends only under the influence of the Earth's gravity. So in this case, say s is the height of the object in feet at say t seconds. So s becomes a function of t, okay? Then what we have is that if we take the second derivative of x, or s rather, okay, then the second derivative or the acceleration of the object is going to be equal to negative 32 in feet per square seconds, right? Okay, and this is actually an equation which is about, a differential equation which is about 400 years old due to Newton. So one of our objectives in studying such equations is such as a differential equation like this, is to find a relation between y and t, where we have a relation between the rate of growth of y with respect to t. So we have the derivative and we would like the value of y. So what we would do here is we would take antiderivative. And in here, let's just use a procedure. It's called separation of variables for such differential equations, that you can see we can have differential of y equals ky dt. Now we have two variables here that we are going to take antiderivatives with respect to t. We are just going in a slightly different style here than you might be used to. So then what I would do is this, that I would bring y together with dy here, and we don't have any t. We could have had a t here, but since we don't, we can just leave the constant here in this case. So what we got is that we got dy over y equals k dt. So what we have done is this, that we have separated the variables. Which variables? The variables y and t. And then we can go ahead next and take the antiderivatives, okay? So here we will take the antiderivative of y, and that equals the antiderivative of k with respect to t. And when you take these antiderivatives, then what we have is this, that we have natural log of y equals kt, and then we will have a constant of integration, that is c. Now we are talking about populations, so let's assume that in our case here in this example, y is positive, or population is positive, so we won't need this absolute value. All right, so we can just write absolute value of y as y, and then you can solve for y now in terms of t. And here in this case, it's easily possible. Now, it may not always be possible to just solve y explicitly in terms of t, but we will handle those cases shortly afterwards. So you can I'm just writing it as as we go by simplifying it. So multiplication is commutative, so I can write it as this kt, and then let's write, say, e to the big C as, I'm just calling it, say, little c. Let's call exponential of big C as little c. Sounds a little awkward, but it's not wrong. So let's just write it like this. So this is the relationship. Now you change the values of c and k, you will have many solutions. All right, so we need more information if we want to find this equation or relation in a particular situation, and we will discuss about these particular situations or particular solutions, okay, in solutions of differential equations shortly. So as a specific example, let's see that, say it's given that 200 bacteria, okay, are introduced in a culture, and the growth of the bacteria follows this exponential growth model, okay. And we have to do this. Now we have to determine the value of C. So this is introduced in a culture, okay. And so what we can do here is this, that we can start our time t, or start the clock, the moment these many bacteria are introduced. So what it means is that when t is 0, then the value of y, or the initial population, is how much? And you can call this as an initial condition. Y at 0 is 200. So we will go ahead and put these values in. Okay, it's 200 here and 0 here. So what you have is, since e to the k0 is e to the 0, which will be 1, so c simply is how much? 200. And then the equation can be written as y equals 200 times e to the kt. Now, if we want to determine k, then we need more information. So say we are gathering the information, and we find that say at t equals, and say t is in hours, okay. So say at t equals 3 hours, the bacteria has grown to 400, all right, okay, or that's the way, say, it doubles. So what will happen now is that we have y equals 200 times e to the kt. We can write 400 for y, for t equals how much? 3. And now we can solve for k, which will be the growth rate. Let me just write it in a form that many of us are used to working with. And then we are isolating k. So what we would do is that we will divide it, or divide the equation by 200. So we got 400 over 200. So e to the 3k is 2. And if we would like to solve for k, then k is sitting in the exponent, who will pull it down for us. natural log because the power is on e here. So we got, sorry about that. We got e to the natural log of e to the 3k is ln of 2. So 3k is how much? Natural log of 2, or k would be 1/3 natural log of 2. And you can use your calculator and obtain that. The value of k is 0.231 approximately. And a complete solution of the equation is, say we chose to round after 3 digits after the decimal sign, so it will be 200 times e to the 0.231 t, and this is the growth rate here, hourly. And in this case, or in other words, in case you want to go from here to 400 directly, this is called double life of bacteria, and we can formulate it in a different form, but just let's stick to what we have at the moment. So now during the first week, or in the case of a winter session or summer session, say in the first 2 days, what we are going to do is that we are just going to go further with our calculus techniques in the context of differential equations and do the solutions by separation of variables. So say, for example, we are given a differential equation like this, okay, which says that we have to solve this differential equation by separation of variables. So what we would do is that we would go ahead and excuse me, and let's move this part to the right, okay, and so that is moved to the right, changed sign. And now what we would do is that we will bring y minus 1 square below dy, okay, and then we have dx, okay, and so what would this give us when we integrate? We will take the antiderivative of 1 over y minus 1 square, and here we have the antiderivative of 1. So what we have is, here if you substitute y minus 1 equals u, then what you are going to get is negative 1 over y minus 1. All right, and here I will have x, and I can put my constant of integration, say c, in this part. All right, so what will happen is we can go ahead and solve it algebraically and say we want to solve y for x. Instead of t, I took x because your book does that. Okay, so let's just take the reciprocals because I have to solve for y. So what would this become is negative 1 over x plus c. I wrote capital C, but you can write a small c if you would like. And here we go. So ultimately our solution is what? Y equals 1 minus 1 over x plus c, and c will depend upon, depend on more information. In this case, say on the initial condition. Okay, initial condition is, that is one way to describe initial condition, is that the value of y at x equals 0. So we will take those up in other example. So now let us take another example, say example 2, in which I am solving a given differential equation, dy dx equals, say, e to the 2x, okay, then plus, say, 7y. All right, so this is a differential equation that's given to us, and we are wanting to solve it. So what we would do is that, well, first let's just go ahead and separate the variables on the right hand side, and you can do that pretty easily here as product of two exponentials. Okay, sorry about that, but anyways, let me write it again. So here we have e to the 2x times e to the 7y, and when we separate the variables, let's move up further. Okay, so what will happen? We can bring in e to the 7y on the left to be with dy, okay, and leave e to the x or 2x dx on the right hand side. And now when we integrate this, and I may stop using the antiderivative sign again and again later on once we get fluent with the procedure. Okay, so here we go. So we have these two, and now again by substituting for this variable in the exponent, what you would get is you will have negative e to the negative 7y, okay, all right, over negative 7, all right, equals e to the 2x over 2, and then we will have a constant of integration. Okay, now first note this, that trying to rush it, I made a mistake here. So there is a mistake in this part here. That is, I did this, I wrote negative twice. If I was writing negative 7 on the bottom, this was not needed. Okay, all right. Now I'm not solving it explicitly for y. If we have initial conditions, we can try to find a particular solution here. All right, but right now we may leave it as it is or rearrange it in a different way if we would like. And now let's take up this example, and again for for a little while we are just doing the calculus review with differential equations. So we are separating the variables. All right, and if you are looking at your book, you may see that it even says that solve this differential equation by using separation of variables. Okay, so here we got x cubed, and then we have I brought dx here. So, oh, I'm sorry, I reversed it, didn't I? So I should have been careful looking at the order. Now if we separate the variables, then here I have x cube ln of x, or natural log of x dx, and that equals y plus 1 cube, all right, divided by y dy. Okay, and now we will integrate the two sides. Okay, and if we integrate the left hand side, what we have is that we are going to take up the integral of this portion, and for the right hand side, that of this portion. Okay, all right, so let's move this up so that I don't have to keep scrolling further. Now for this integral, if you just play with this for a little while, you will see that this connects with what you did as the integration by parts, where you had u dv equals uv minus v du. All right, and in this case, I think it will be more appropriate to choose our ln x as u, okay, and x cube dx as dv. Okay, so what we are going to do is this. We will take u equals natural log of x, which will tell us du equals how much? 1 over x dx, right? And at the same time, we are taking, let me do that in the next line. Okay, let's take dv as x cube dx, okay, which is, and that is going to give us, if we integrate both the sides, and I'm not using the integration symbols, that we have quite matured into that, and I'm ignoring the constant at the moment because we are going to put it at the very end. So v is x to the 4 over 4. So what we got is that we have x cube natural log of x dx, the same as this, and that equals uv, and who is my u? U is natural log of x, right? And who is v? V is x to the 4 over 4, so I can write it right here. Okay, I'm just using the commutativity of multiplication, and notice this, that I'm writing uv as vu here. So hope that you are not finding it confusing. All right, and then what I would have, let me put integral sign here, then I will have v du. So v is who? V is right here, and du is what? We just had our homework done here, or okay, that is 1 over x dx. So what we get here is that we have the answer as, we will have x to the 4 over natural log of x, and then minus, here we got x cubed over 4. Okay, all right, dx, and that is going to be simply x to the 4 over 4 natural log of x, right? And then minus x cubed, the antiderivative would be x to the 4 over 4, and that 4 when joins the 4 on the bottom will become how much? That will become a 16. So that's going to be this integral here, right? Okay, now we have to obtain this integral. Okay, now for this one, we may do this. Now we have a review of calculus as well as that of algebra 2. Okay, so we will go ahead and expand y plus 1 cubed. Okay, all right, so that's what this becomes. And then, so this is the same as the antiderivative of this whole quantity over y. And then what we can do is, in this case, I think a good strategy would be just go ahead and divide by y. So you get what? You get y squared plus 3y plus 3, and then plus 1 over y, okay, dy. So if I use this portion here, then what the antiderivative of this part is going to be, we will have y cubed over 3, okay, then sorry, no, why am I sorry? That's correct, I'm integrating this, right? Okay, then for y, I'll have y squared over 2, so that would be 3 3y square over 2 plus 3y plus 1 over y would be natural log of absolute value of y, and we can put a constant here. We did not put a constant in this portion. If we had, we could combine the two constants together. So let's bring in our original differential equation. So we have the equation like this. So the left part is what? The left part is this portion, and the right hand side is this. And again, we are going to leave it as it is. All right, and I'm not even going to attempt to write y in terms of x explicitly. So let's just leave it implicitly, and if we have to do it for an initial condition, we will do it later at that time. Okay, so now again what we are doing is that we are still reviewing our techniques from calculus. Okay, so say we are given this differential equation, and instead of dy dx we wrote dp over dt, that is p is changing with time. Let's just make it 4 if we don't mind. Okay, all right, so in this case, if we separate the variables just as we have been doing, we have p minus 4p square here, and what we got here, we got simply dt, and then when we are going to integrate, then the right hand side is pretty simple and straightforward. That is going to be simply t. But for this one, where we have to integrate 1 over p times 1, or rather p minus 4p square. So what you have here, you have a rational function. Okay, and so what you attempt to do generally is this, that you would try to factor the denominator. Okay, it's just one way of doing it. So this will become 1 minus 1 over p times 1 minus 4p. Okay, and then remember how you handled this. You just went ahead and assumed that this can be written in partial fractions. All right, so this is b over 1 minus 4p. All right, and then we just go with the typical procedure the way we had to determine the coefficients for partial fractions. So what I would do is that we are simply going to take common denominator on the right hand side now. So what you got here is, you got this 1 minus 4p right over here. Okay, and then I'm going to take the same denominator on this side. So we have a p, and we will put a p up here to balance everything. All right, and again, as I said, this looks like more of a review of algebra 2 at the moment. So anyways, I'm going to let these guys rest on the above the same denominator after we did this work. And now what I'm going to do is that I'm going to open the brackets, or distribute the quantities over the brackets. So what do I get? So here, when I multiply a with 1, I get negative a, then I get negative 4a times p. Then we would do this, that we will collect the like terms. All right, so what that gives us is that 1 minus 4a, oh no, just a moment, I went opposite. Actually, when I'm doing this in class, there are always some people who just show A and B as show and tell. All right, but right now we don't have a live participation, so I have to keep on looking at it. Okay, so plus B, P. What I did was that I combined the terms involving P together and the constants separately. So what does it give me? It gives me this. A is a constant. How much constant? So the only constant in here, see these two match here. So the only constant in here is A. So A is how much? A is 1, right? And for this guy here, this is coefficient of P. We don't have any P here. So which means what? That my P is how much here? 0 in quantity. So if that's the case, then what we have to obtain that as is this, that negative 4A plus B is 0. Now we just found that A is 1. So what we have is that negative 4 plus B is 0, and that gives us what? B is simply 4. Okay, so when we write this as partial fractions, or A over, just a moment. Okay, so when we wrote this as A over P plus B over 1 minus 4P, then with these values of A and B, what we have is, we got this as 1 over P plus 4 over 1 minus 4P, right? Okay, so what you have to obtain there is the antiderivative of this, or the indefinite integral of this quantity, I'm sorry, dP. Okay, so that will be 1 over P dP plus, next what we have, 4 over, okay, over 1 minus 4P dP, right? Okay, and this would be what? The first quantity is ln of P, right? And in the second one, what you have is, if you take 1 minus 4P as another variable, then 4 dP will become d of that variable. That is, if I took this as W, 4 dP would be dW, and negative dW rather. So that would become what? ln of absolute value of 1 minus 4P, right? Okay, so where did our original equation go? It's right here. We were looking at this, and so let's bring it in here because we are almost done with this. So, and then this becomes equal to, the antiderivative of 1 is simply t plus a constant c. Okay, so that's what. So here what we did was we simply reviewed quickly the technique of integration by partial fractions. Okay, so now let us work on differential equations in which still the variables are separable, all right, but we have initial condition given. So in this case, for example, say we have this differential equation. So what we can do is that we can bring x squared plus 4 here, so the variables involving x on one side, and then we have the antiderivative of 3 with respect to t on the other side. Now, so here you recall this, that this is just the 1 over x squared plus 4 is derivative of, if you recall your inverse trig function calculus, okay, then what is this antiderivative? 1/2 tangent inverse of x over 2, right? Okay, and then on the right hand side, what we have, we got 3t plus c. Okay, now when t is 0, x is 2. So what we would do is we will substitute those values in. All right, so here I have a 2, my t is 0. Okay, and then what I get as a consequence of this is that 1/2 tangent inverse of 1 is going to be c, and who is tangent inverse of 1? That's pi over 4. Okay, so it's 1/2 times pi over 4, okay, is our c, right? Okay, so, or in other words, c is simply pi over 8. Okay, so what we get at the end is that we have 1/2, all this equals, c is pi over 8, so we will write it in here. Okay, and then this gives us that tangent inverse x over 2 is, we are going to multiply the right hand side by 2, so what we shall get is 60 plus, and then 2 times pi over 8, of course, would be pi over 4, or in other words, you can write that x over 2 is tangent of 60 plus, just a second, yes, here, tangent of 60 plus pi over 4, or here we could write x explicitly as a function of t, right? So tangent, let me just copy paste this thing. So here is our explicit solution of this differential equation with an initial condition, and which we also call an initial value problem. All right. Now let us do the last example of this lecture. That is, we are going to solve this initial value problem, and so we are just visiting more of calculus techniques than doing anything new. So, and again, we are hoping that it is still an equation with separation of variables, okay? All right, or where the variables are separable. So here we can still do that. So we have dy over y equals 1 minus x over x square. Okay, so what we have is, or we can, and then of course we have a dx. Okay, and then we can simplify it further. Okay, and if we do that, what we have is that we have 1 over x square, all right, minus 1 over x. Okay, all right. Now when we integrate the two sides, what we will get for this is that we will get, oh, no, sorry, not yet, natural log of absolute value of y. The antiderivative of 1 over x square is negative 1 over x. And here what I get? Minus natural log of absolute value of x. And then I have plus a constant. Okay. now we have this initial condition given, right? Okay, so what does that mean is this, that we are in a neighborhood of -1, -1. So what we mean is the following. So again, our situation is this, that we are solving this initial value problem and we are looking in a neighborhood of -1, -1. So what that means is this, that we can just confine ourselves in a neighborhood of this -1 and -1, or -1, -1, the ordered pair, or in other words, we can assume that both our x and our y values are negative, around the point -1, -1. So if we go back to our example, so we can note here that both the variables x and y, both of them are less than 0. So if we go for solving for this, what we have is, let me bring it over here, it changes sign, right? Okay, sorry about that. And then what I have is that this would be the left hand side, the sum of natural log of two quantities is the natural log of their product, right? So by that we are going to have natural log of absolute value of yx equals -1 over x plus c. Now since both x and y can be taken as negative here, we can ignore the absolute value sign, right? Okay, and we got epsilon of yx equals this, and the initial condition. Let's bring the initial condition in. Okay, all right, the initial condition is what? That y at -1 is -1. Okay, so x and y, both of them will be -1. So what we get is this product will simply become -1 times -1, that is 1. And then negative of -1 will be 1. So natural log of 1 is 0, and that what that gives us for c is -1, right? So what we got is that, yes, let's scroll up. Okay. All right. So this becomes -1, or in other words, we have, let's take a negative out as a common factor. So we get 1 over x plus 1 here, and then we have xy or yx equals e to the power this value. Okay, and our answer would be then what? Y equals, okay, 1 over x, okay, times this exponential function, and that's our final solution.